So yeah, that's true, but we're not the moon or the sun. We're an observer in a different frame of reference. If you're in the spaceship, it's your photons being given off. So perhaps it would appear stretched, maybe, but you're the one giving off the light that you're seeing. If that makes any sense. So
okay, don't know.
So perhaps
we've started an argument here. We're gonna have to.
Yeah. Okay. Let's. I'll think about this one.
All right. Okay.
I'll have a think. But yeah, I'm
sticking to my guns on this one.
Yeah,
I know I'm not a PhD student, but I reckon.
Yeah, I mean, you might be right, to be honest. But yeah, my assumption would be you would see an empty dock, but somebody else on Mars who wasn't on your spaceship.
Well, somebody's standing next to you. So you've literally just got off your spaceship, and I don't know, Zaphod Beeblebrox is stood next to me, and he can see me setting off, but I can't. That doesn't make any sense.
Well, okay, let's put this. Let's agree to disagree.
Okay,
let's move on. Yeah, I don't know is the answer. I'll have to think.
Right. Okay. I'm not satisfied with that, but we'll move on.
We'll move on.
Hello, welcome to Matter Over Mind. My name is Stephen, and with me, as always, my favourite son-in-law, Thomas. Hello, Thomas.
Hello. How you doing?
I'm very well, thank you. So we, as you may know, you may not know about this podcast, but we each episode, we cover either a physics episode or a psychology episode. You're doing your PhD in plasma physics at Oxford, yes. Thomas, and I'm an organisational psychologist. So we kind of draw on those sorts of things and what we know, and also do a bit of research along the way. Don't forget, if you like this type of stuff, then subscribe to the podcast or the YouTube channel. So that would be great if you could do that. It's your topic today, Thomas. What are you going to tell us about today? And we're going to sort of take the heat down a little bit, although it is roasting hot in the UK. We're going to take the heat down a bit because we're going to talk about something a bit fun.
Yes.
And that is what?
So it's physics movie myths. So those of you who have listened to season 1 will know we did a psychology movie myths episode. We did. But now we're going to do the physics version. Yeah.
You just got jealous because of the fun times we had with the physics one. You thought, I want to do that.
Exactly. Yeah, that's exactly right. And also now this is probably true for anyone in any profession. When you see that profession on screen, it's always a bit naff. So there's loads of stuff in movies that kind of make me cringe when I watch them because they're either horrendously bad or they're just kind of very buzzwordy but doesn't really mean anything. And even though no one else really seems to care, I do. So I've got a few topics of just sort of general pieces that kind of pop up that I thought I might mention, and then I've got a few specific movies that have notorious science in them.
Okay, off you go then. Let's see your first one.
Okay, so the first one is probably quite an obvious one for most people, but space in movies often doesn't make any sense whatsoever. Now you could argue it's for movie effect. You know, you can't have it all super realistic, but there's a few things that just kind of grind my gears a little bit.
Okay, tell us what are some of the things that they get wrong then about space?
So the first one is this idea that if you fall into space, you're going to instantly freeze. You're going to turn into a block of ice straight away. Yeah. That's not true. That would not happen. Okay. So when you heat something or cool something down, there's kind of two main processes. There are some edge cases, but either it's radiative cooling or heating. This is where you just emit radiation or absorb it to heat up or cool down. So if you look at someone through an infrared camera, you can see they're just giving off radiation ambiently. Okay. Generally, that's quite a slow process, at least compared to the other kind. The other kind is collisional heating or collisional cooling. This is where stuff hits you, absorbs your energy, and then kind of takes it away. So if it's really windy, for example, the wind hits you and you feel cold, what's actually happening there is the cold wind is striking you, it's absorbing your thermal energy, and then it's carrying it off, so you've now cooled down. So that's collisional heating or cooling. So that's generally a lot faster than radiative cooling. So in space, it's vacuum. There is nothing.
There's no wind. There's not wind.
There's no wind. There's no medium to cool you down. The only way you're cooling down is by just radiating heat. And unless you're a stellar object that's, millions of degrees, you're not going to be radiating that much heat. So you'd actually cool down very slowly in space, and it probably wouldn't feel cold. There's a bunch of other nasty stuff that would happen first, but you're not going to freeze, basically.
You're not going to freeze to death. That's good news. Okay, I like that. Yeah. Good news. What's the bad news?
The bad news is, so space is very low pressure. It's a very low pressure environment because there's nothing there. Pressure is pressure is a thermal property. So, for example, if atmospheric pressure is usually sort of attributed with at sea level, that kind of thing. And basically the pressure there is the air around us, the gas around us is kind of keeping everything compact. Exactly. Yeah. So, I mean, you've probably had it if you have like a fizzy bottle, you shake it up and close the lid. It's very hard to kind of push. So that's obviously, you can think of pressure in the kind of kinetic description of pressure. And this basically is, imagine you've got an air particle bouncing against the container. So, the impulse it imparts, so that the change in momentum as it hits that container produces an outward force. That's pressure. Pressure by definition is force divided by an area. So how much force you exert on a particular area, that's the definition of pressure. So you can imagine all the air around you is kind of bouncing off of your skin continuously, kind of keeping everything at bay. So why that matters, who cares if space is not pressurized? Well, it turns out that the boiling point of liquids, for example, is very tied in with pressure. So at very low pressures or very high altitudes, for example, water doesn't boil at 100 degrees anymore. You might be able to go up a really tall mountain and it might boil at 87 degrees, say. So the lower the pressure, the lower the boiling point of water, or just a liquid, some arbitrary liquid. Most of us is water. We're about 70% water, right?
Right.
So if you chuck us into a zero pressure environment, suddenly there's nothing, we're not pressurized in the same way. So our blood and our fluids will start to expand and, I guess, boiling, despite being a relatively cool temperature. So that's not going to be great for a person.
So I've heard this before. So they talk about it boiling, but it's not hot. So it's not gonna. We're not gonna feel the heat element, are we? We're just gonna feel like our body is sort of bloating out. Is that right?
Yeah, I guess. I mean, you're not going to pop like a balloon. I mean, I think that the movie Event Horizon has a scene where a guy falls into space, and from what I remember, it's pretty grim. It's a pretty gnarly scene. I don't know if that quite would happen. I think you just kind of bloat and expand a little bit. But yeah, so boiling. What I mean by that, the heating part is, I guess, just a mechanism to allow the boiling to occur. It's what's called a phase transition. So it's the transition of phase between a liquid and a gas. The transition of that phase is boiling. And interestingly, while something's boiling, it's at a fixed temperature. So the longer something's boiling, it doesn't mean it's heating up. So water boils at 100 degrees. If you keep the kettle on, if you hold down the switch, the water is going to stay at 100 degrees. It's not going to go above that, assuming you've not messed with any of the pressure. It's just in the kitchen, if you just keep your kettle on, the water will boil away, but it will stay at 100 degrees. So it's an interesting property of phase transitions. Phase transitions generally occur at fixed temperature. But yeah, so in space you wouldn't freeze, you'd boil.
Okay,
there we go.
Well, that's interesting. So that's the first one. Okay, so some films get this right. I think some TV shows. I remember watching The Expanse. I think I mentioned this in our last episode. And this woman, she has to go out into space with her spacesuit on, but she doesn't have. I think she doesn't have a helmet, if I'm right. And she calculates how long she could survive. And that sort of the way that was described was very similar to what you just said. So, well done, those guys. But yes,
Yeah.
often you get these. They sort of turn to ice, don't they? And then they hit something and
Kind of
break
break up.
apart. Of course, yeah. Okay.
Yeah.
So that's one. Any more? What have you got next for us?
So still on space. Just one kind of last
Yeah.
point is, in a lot of movies, I see in space is kind of treated like a liquid. So, you'll be in your spaceship. Oh no, I've run out of fuel. I can't keep going. And then the ship kind of just like stops and kind of starts floating about. That doesn't make any sense. Why that happens if you're a submarine in water, why that happens is because there's a drag force to do with the friction of the water around you. So in space there is no drag force, there is no resistive element. So because of everyone's favorite Newton's third law, every action has an equal and opposite reaction. But another way of saying that is this isn't Newton's third law. I guess it is, but it's also Newton's first law, which is a body will remain at rest or constant velocity unless acted on by an external force. So in this case, external force would be drag. So you've run out of fuel, your thrusters aren't working anymore. You're going to keep going at that speed. Whatever speed you reached when your fuel ran out, that's the speed you're going indefinitely until a big asteroid or whatever gets in your way. But yeah,
Okay,
you're not.
So there's a question I'll have about this because I've often thought about this when I'm watching Star Trek or something like that. When the engines go down, there's this idea that the spaceship will slow down, and I've always thought that doesn't make any sense because of what you just said. There's no atmosphere or anything to act upon it, no friction, so it's just going to carry on. So would it literally carry on until it hits something, or is there enough of something in space that would slow it down very, very gradually, or is it completely sort of empty?
So space isn't actually completely empty, but it's as close to empty as you can get.
Yeah.
I can't remember the number, but it's something like one particle in every square meter or something. It's a really small thing. So it would be so negligible.
Pretty much forever.
Yeah, pretty much forever, unless something blocks your path.
So the Voyager spacecrafts of the Voyager 1 and 2 are still going, as far as we know, and they carried on beaming back messages to tell us that they were still there. There's a great documentary about this, by the way. I forget what it's called now. I might try and find it and stick it on the show notes because it's absolutely brilliant. And you know what? It kind of makes you choked up in the end because you've been with this spacecraft for so long and it's been faithfully sending messages back. And eventually they have to say, well, we're going to have to switch it off now. It's basically that's it. We cannot. It's not worth keeping it on and listening any further. So. But it's still going, I suppose. It's still going in space. Okay, cool. I've got another space question that I didn't prepare you for, so you might. Yeah, I'm sure you do know the answer. But so often there's explosions in space.
Yes.
And there's quite a bit of a debate about whether you'd hear any explosion. Now, I understand, of course, there's no air and sound travels through a medium, so you can only hear sound because it's in normal situations it's airwaves vibrating and it hits your eardrum and all of that. But if you're a spaceship, if you're in a spaceship, then that spaceship is likely filled with air if it's a manned mission.
Sure.
So if it was to explode, would the sound of the explosion it would happen as long as the air was sort of close enough to the spaceship, at which point, obviously, then it would dissipate. Is that kind of what would happen?
Yeah, I get. Yeah, if you were in the spaceship that blew up, and supposing you didn't die immediately, you would hear something. And if you were in the blast wave quick enough, then I guess so. So sound, I can't remember the exact scaling it has, but sound travels faster. It's proportional to density in some manner. So, for example, if you knock on a table, the propagation of a wave due to that tap that sound wave, or it's called a phonon in a solid, but that sound wave travels a lot faster in a solid than it does in liquid and than it does in air.
I remember doing that at school. That's in my Physics for You book up there. Look, the orange
nice.
one. Professor Messer taught me that.
So I guess a way you could think about it, if you're purely just doing the analytical maths of it and you don't care about the physics, purely just on the mathematical relation, you could argue because there's nothing in space, there is no density. And because the speed of sound is proportional to density, the speed of sound is zero in a denseless material. So as the cloud of, or as the ship blows up, whatever air was in it, as that dissipates, the more it dissipates, I guess the slower the sound travels, therefore the less you're going to hear it unless you're really close to it. So you won't hear an explosion in space unless you're actively in the material that's exploding.
Okay.
Yeah.
Interesting. And of course, things like the sound of engines, the sound of rockets, and all of that, which all of the sci-fi films do. I was listening to Brian Cox, actually. He's the UK sort of physicist communicator in chief. He actually was a consultant for a film, one of Danny Boyle's films. What was it called? Sunshine, I think it's called. And he was saying that, he told them you can't hear rockets in space. That is not right. But when they did it, it just didn't look or sound right. You kind of have to put it in. The only film that doesn't do that, I suppose, is Interstellar, Modern One, or 2001, which gets away with it because it's got the classical music. That kind of just it doesn't matter that you don't have sound. But I think it's quite interesting that our sensibilities are so much there that we really want to hear a sound, that as the spaceship flies past the pretend camera.
Yeah, I mean, I guess that's probably why also they portray spaceships as if they're traveling through a fluid of some kind, because it just makes more sense to us that if you run out of fuel, you're going to slow down, or if an explosion
air.
happens,
I suppose I think they treat it like air in a way, because they're performing the sorts of flying that you would see in an aeroplane. I guess that's kind of what you're seeing.
Well, that's why I was careful with my wording. I said fluid, not liquid. That was
okay.
That was a deliberate choice there.
Okay, what's next then? Tell us what's next.
Right, so the next one is lasers.
Okay, my favourite. Yeah.
Lasers are very cool, and in movies they're kind of just magic, really. They kind of just do whatever the film wants them to do. So everyone's seen the classic spy movie thing where they kind of do acrobatics in the laser room to dodge the, either. So that's cool and all. There's a big flaw in most of these movies is you can't see them. Right now, some of them they spray the little canister, but most movies you just see these red beams. So why you can see them when you spray like an aerosol at a laser, but you don't otherwise, is because lasers, they have this cool property, which all the light they give off is in one direction at one frequency and one wavelength and one, and so on and so on, which means you don't have any diffusion of the beam if you have a good laser. So when you spray an aerosol at one, what happens there is you've introduced a medium that scatters, parts of the weight of the laser, and then as you scatter it, it diffuses around. So that's why you can see it. Generally, lasers travel in a straight line, so you're not going to see the beam unless something scatters and diffuses it, which is what the aerosol does. So in reality, if you went into one of these super secret laser rooms, there'd be a bunch of red dots on the wall, and that's probably about it. So you'd just be dancing in an empty room, which would probably look a little bit silly.
You couldn't even see it, let alone be able to dodge it. You couldn't even see them.
Yeah, exactly. You'd see the spot on the wall, but that was about it.
Yeah. Okay. So that would also go for like laser weapons, wouldn't it? So I know sometimes they call them blasters, so they kind of get away with it because who knows what a blaster is really. But when they're lasers, you wouldn't actually see the chung 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 chung. You wouldn't see that. It would just be one continuous shot, but you wouldn't even see that. It would just be like an invisible beam, and you'd only know it was on. Well, you'd only know it if it had hit you or something near you, I suppose. So,
which would also mean, you know, in like Star Wars when they're dodging the stormtrooper, you wouldn't be able to dodge it because it's light speed, isn't it? It's instantaneous.
You would have to move faster than the speed of light. Okay, well, while we're on Star Wars, what about lightsabers? Tell me some problems with lightsabers.
So lightsabers, they're not lasers. They're kind of called these, you know, laser swords. No, the lasers don't do that. You can't. If you hit something with a laser, it's not going to bounce off of it like the sword, you know, like the lightsabers do, right? It's just gonna. I mean, lasers. It's just light. You wouldn't hit something with a torch and bounce off something, right? Now I've heard some people. Yeah, sorry, go on.
I was going to say how, like when they turn it on, it goes, you know, it comes out so far and then stops, and I've always like, how did they do that?
So some things I have heard people talk about in, you know, when this kind of gets brought up is they kind of mention it's probably more like a plasma than it is a laser. You know, you can confine plasma with magnetic fields and stuff, which so yeah, I mean that's a more viable. It would be extremely hot, and holding it, you know, inches away from your hand probably wouldn't be a if it's. Yeah, I mean, if it's giving off that much light, it's going to be extremely hot. But yeah, so the closest thing I guess it could be is something like plasma, or if you put like a little like mirror on the end of it and then shone the light that bounced back and forth, I guess that would stop it going off forever. But yeah, lightsabers, unfortunately, it's just nothing to do with lasers. Yes.
Okay, I'm on a roll now, so I know you got some stuff prepared, but I'm really into this now, so I'm going to ask you another one. Now, obviously, I know that the transporter machine in Star Trek and lots of other sort of sci-fi's that seems like it could never happen. But I understand that there has been some experiments that suggest that, you know, theoretically anyway, you can transport a sort of single subatomic particle or something. But anyway, tell me about transporters. What's the problem with transporters?
Well, so you would need an object that. Well, I'm assuming this is how they work. I don't know if they explain it in these shows and stuff, but I'm assuming this is probably what they do. They zap them with something that takes all of their physical, you know, material information, and then turns it into some information, whatever that means. Transports it like a radio wave or some kind of, you know, EM signal, and then reconstruct it once it gets to the other side. I'm assuming that's how they work.
Yeah, that's pretty much it. There's a pattern buffer in Star Trek. And the pattern buffer is where they store the data for the person. So there's a little story I tell Celine and Sarah about this. On one of the programs I was watching, one of the guys that came up with, a lot of the techie talk in Star Trek, they go to these conventions, and he said, Pete, there's always somebody that comes up to me and says, how do the Heisenberg compensators work? So there's this term in Star Trek called the Heisenberg compensators, which obviously gets around the problem that you can't really know enough about a particle in order to basically put it where it needs to be back in to make a whole person again. So how does that work? And he said the only answer to that is very well, thank you. Which I just think is a brilliant answer. How do they work? Very well, thank you. Because obviously it's science fiction. But anyway, that was just a chance for me to tell that funny story.
I like that answer. I might steal that one next time I'm asked a tricky question at a conference. How does that work then? Very well.
Very well. So okay. So anything else to say about beaming? I mean, obviously there's a problem in that when you transport from normally anyway, normally sci-fi, not all of them, because sometimes there's equipment at both ends, but like in Star Trek, for instance, they have all this equipment at one end. They stand on the transporter pad, and as you say, presumably it disintegrates, kills the person essentially, disintegrates them, and then reconstructs them. But the reconstruction bit is done where there is absolutely no equipment whatsoever.
Yeah.
Yeah, they just appear. So that's a problem. And of course, the other sort of metaphysical question is, like, when Captain Kirk disappears on the transporter pad and reappears somewhere else, he's actually technically a different person, really. So is it about, are they basically killing the crew of the Enterprise every single episode? They think they're the same person when they reappear, but they're not really. So anyway, that's another problem.
Some moral questions there. Maybe save that for the next psychology one.
Some ethical questions. Yeah. Right. Okay. Also, so I've interrupted your flow. Go on.
No, I've kind of thinking about that now.
Okay.
So one more point on this, I guess. So
okay, cool.
Yeah, so they turn them into information and zip them across a planet or whatever. Well, so the spaceships have warp drives to get around the faster than light travel thing. But if you're sending, an information signal, that's going to be electromagnetic radiation, which travels at the speed of light. So they're going to take ages to get anywhere. They send them, then over to the next, solar system or whatever. It's going to take them thousands of years to get there.
Yeah, I don't know. They don't normally send them very far. We're deep into Star Trek lore now, and even I feel out of my depth at this point. So I think maybe we leave it there. But yeah, it's I mean, it's a good device. Apparently, they invented it because they couldn't afford the cost of models for shuttlecrafts for the Enterprise. Okay. So it's just so easy if you've got this device that just beams you from one place to another. You don't need to worry about shuttles and all that sort of stuff. So sounds like a good idea.
Yeah,
okay.
Makes sense.
What else have you got for me then, Thomas?
Okay, so before we move on from lasers, everyone will probably be thinking of that famous 007 scene. I think it's GoldenEye was the movie where James Bond is strapped to this bed, and then the villain wants to cut him in half with his laser. And he turns it on, and it kind of moves really slowly and starts slicing the metal bed in two. So I watched that scene the other day specifically just so I could make sure my science was right. Now, lasers for cutting things is a thing. Now that does happen. Yep. You can have industrial machinery that does cut, sheet metal and what have you. There's a few differences when they do it in reality versus when they've did it in this movie. So, First off, there's no shielding anywhere. So, no one's wearing their goggles. Nothing like that. So there's a bunch of health and safety
problem. Yeah. Okay.
Yeah. I mean, when I started my PhD, I had to do some serious training for laser stuff. It was it was like a 2-hour seminar, the classic, and then it's like we'll send around a test for you to do, and if you need to get above 90% or whatever for you to pass this training. Otherwise, you need to do it again. Okay, fine. Right. So I was kind of expecting just like a multiple choice. No, it was like a proper exam. It was like if you have this class of laser with this material crystal, and this is a catalogue of goggles you can buy. Can you use this laser safely based on, and prove it based on the optical density of the goggles supplied or something? So I had to really actually do some pen and paper calculation to show that. Yeah.
Baddie in James Bond, nor his henchmen have ever been on that course.
Probably not, no. But yeah, it was a really boring course and I didn't want to do it again. So I made sure to study and pass. But yeah, so first off, no one's wearing goggles. Everything's just, open plan. But the main problem, so James Bond's there, quipping and being all suave and what have you.
Yeah.
But the laser's coming in at a really steep angle. It's coming at like a 45-degree angle to the bed. So I've said this already. Laser is just light, and metal is reflective. Particularly if you're optical wavelength lasers, you're just going to scatter. You're going to bounce off. So while James Bond is sitting there being all cool and talking his big talk, the laser's going to reflect off the bed and just get him anyway. So you don't need to wait. Also, as the gold, or it's not the gold, so the metal bed starts melting, that's going to now scatter the laser light and all. So everyone's going to get got. That's why you have proper laser shielding, folks.
Right. Okay. So take note if you're an evil genius thinking of using that as a device to kill your nemesis.
Yeah. Exactly.
Okay, cool.
Okay. So
what's next?
The last one on just generic movie stuff. Like obviously there's loads of generic movie stuff, but the last one I've got here is, so in typically action movies, you've got a guy who's running around, running and gunning. He's shooting a bunch of people. And there's always that particular scene where he's standing there, he says his one-liner, and he shoots a guy, and the guy gets thrown 15 feet back, through a table or something. But the guy's just standing there, unperturbed by this.
Right. Okay.
So, a couple of things there. If you shoot somebody and they fly back 10 feet, well, that force also has to have come through your arm. So you're also going to be, shunted back a reasonable amount.
So if it's powerful enough to throw them 15 feet backwards, you should have felt the same force in the opposite direction. Is that right?
Exactly. Yeah, that's Newton's third law. If a body is exerting a force on something, it will exert the thing it's exerting a force on will exert the same force in the opposing direction. Basically, every action has an equal but opposite reaction. So the guy shoots somebody, that recoil is going to have to be powerful enough to throw him back the same distance the guy who got hit gets thrown back. Otherwise, that's just not going to happen. Also, it's a thing about pressure again. A bullet is, I've never seen one in real life, but I imagine pretty small, very small radius. I don't know, the size of a coin, say. So if it's powerful enough to knock somebody off their feet and to push them far back, then the force exerted is going to have to be at least equivalent to their weight, right? But the difference now is the surface area of the bullet is really small, so the pressure is going to be really high, which means it's just going to zip straight through somebody. It would be like, if an elephant steps on your foot versus an elephant wearing a high heel steps on your foot. The elephant's foot's just going to crush your foot, the high heel's going to go straight through. Yeah. So if a bullet holds enough momentum to knock somebody 10 feet back, because of how pressure, force, and area are related, it's just going to go straight through them, and they probably wouldn't even be knocked at all. It's just going to zip straight through them. Yeah. So
okay,
a myth there.
Yeah. So the whole it could be a psychosomatic reaction, I suppose. Maybe they're just jumping backwards.
Maybe
because they're expecting it. Maybe they're doing it, I suppose. Is the
yeah, that's true. Maybe it's just for show.
Okay. So that's interesting. So you've not mentioned any time traveling ones. Probably wise. It's a bit of a minefield, isn't it? They all get it wrong. All the films, because we don't really know how it could work. So I suppose that's just
Yeah,
the one that I always laugh at is the Looper film, the film Looper, where the guy is I can't remember how the scene starts, but he's walking somewhere, and gradually, in the past, his fingers and toes and feet and hands are getting cut off. Yeah. And so he's gradually losing all his limbs, which is awful. But that's just complete and utter bunkum. I don't know how on earth that could ever work. But anyway, it is quite funny in a very sad and dark way. Okay, cool. There was one thing I think I mentioned this when we were talking when you were over here last. So, and I don't think we got a proper answer for it because I'm not sure there is one. But so if you're traveling faster than light, so say you've got a warp ship which gets around the speed of light, problem in that you're bending space, which means that your getting around the law that says you can't travel faster than the speed of light by bending the space.
Yep.
Effectively, it means you're getting from one part of the galaxy to another quicker than you would if you were traveling the speed of light. So
Yeah.
let's say you go from Earth to Mars.
Mm-hmm.
You've got some amazing technology that can warp the space between those two bodies.
Mm-hmm.
You leave Earth, and you very quickly fold space, and you get to Mars almost instantaneously.
Mm-hmm.
If you then had a really strong telescope,
Yeah.
and looked back from Mars to Earth,
Mm-hmm.
let's imagine there was such a telescope, you could actually see the spaceship. The spaceship would still be in the hangar, not having left. Presume it's a spaceship that's going faster than the speed of light, if you see what I mean. So
Yeah.
my point is you would actually observe yourself before you'd set off. That's right, isn't it? That's how it would work, because you'd be observing Earth at the speed of light. You'd be observing the light particles hitting your telescope, but they're only traveling at the speed of light.
Yeah. Yeah. Yeah.
So you're getting them, however many days or hours. I suppose it's hours for Mars, but well, we know that it's about 20 minutes each way, isn't it? Or 40 minutes, I think we said, from our last episode. So you'd see it sort of 20 minutes ago or 40 minutes ago. Is that right?
I think in principle, yeah, I think that's the idea. I mean, the idea of the speed of faster than light travel is, an issue with simultaneous events and two observers disagreeing with when something began. Whether you would see yourself, I don't really know, because
Well, you'd see the Earth as it was. I think it's 20 minutes, isn't it? That sound takes light waves take, because we said that radio would be 20-minute delay when you're on Mars, and then another 20-minute
20 minutes,
the other direction. So if you just talk about one direction, it's 20 minutes it would take for the light to reach Mars. So if you, as soon as you get there, you get your super fast telescope out and you have a look, then you're seeing what the Earth was like 20 minutes ago.
Correct, yes.
Not what the Earth is like now. So you're seeing what the Earth is like 20 minutes ago, which would include, if it was strong enough, you taking off from the Earth.
So I think that's almost correct. But you would need a secondary observer. I think how it would work is this. You on the spaceship, or once you've got there, you would perceive that distance as shorter than it actually was. So to you, I think this is possibly how it would go. Well, obviously this is all kind of a bit thought experimenty, but I believe this is probably the slightly more accurate way of thinking about it. To you, you've reached Mars, so even if you had a powerful telescope, you see you've left the dock. But somebody maybe already on Mars, or maybe not yet at Mars, to them, you've not left yet. So you would look back at the telescope, and it, because you've stretched space or compressed space such that you can get there in time. So you see, I guess, an empty dock because you've left. But another observer, perhaps even still on Mars, will get that light signal, but you've not left yet. So that's where the paradox comes in. To you, you're like, well, no, I have left. Look, I'm missing from the dock.
But how can that be? Because you're only getting the light as it was 20 minutes ago. It's taken you like a fraction of a second to reach Mars. Yeah. So effectively, you've travelled faster than the speed of light, technically, or in terms of you've got there quicker than light would get there. So you're 20 minutes before you've set off, essentially. So you're looking back at the Earth, and you're seeing the Earth as it was 20 minutes ago. Just like if the sun went out now, if the sun exploded or something, we wouldn't know it for the first few minutes. I don't know, is it 8 minutes or something like that?
Yeah.
Or if the moon just disappeared, we wouldn't know that for a minute or so.
Yeah.
Because we'd only know it when the photons reached our eyes. So, as I say,
Yeah.
that has to be the case.
So yeah, that's true, but we're not the moon or the sun. We're an observer in a different frame of reference. If you're in the spaceship, it's your photons being given off. So perhaps it would appear stretched, maybe, but you're the one giving off the light that you're seeing. If that makes any sense. So
okay, don't know.
So perhaps
we've started an argument here. We're gonna have to.
Yeah. Okay. Let's. I'll think about this one.
All right. Okay.
I'll have a think. But yeah, I'm
sticking to my guns on this one.
Yeah,
I know I'm not a PhD student, but I reckon.
Yeah, I mean, you might be right, to be honest. But yeah, my assumption would be you would see an empty dock, but somebody else on Mars who wasn't on your spaceship.
Well, somebody's standing next to you. So you've literally just got off your spaceship, and I don't know, Zaphod Beeblebrox is stood next to me, and he can see me setting off, but I can't. That doesn't make any sense.
Well, okay, let's put this. Let's agree to disagree.
Okay,
let's move on. Yeah, I don't know is the answer. I'll have to think.
Right. Okay. I'm not satisfied with that, but we'll move on.
We'll move on. Okay.
All right. What else have you got for me then?
So now I'm going to get into specific shows or movies. Okay. So there's a couple that have bad science, and then I'm going to mention a couple with some good science. And the final one I'm going to mention, the science in the movie makes more sense than what I'm actually going to talk about, because I think what I'm going to talk about is cool. So that's a little thing for later. Okay, so the first movie is Ant-Man. The Marvel movie that came out, I don't know, a while ago now. But for those of you who don't know, the plot of the movie is a guy's got a special suit and he can shrink himself to very small or expand himself to very big. Now, in the movie, it explains it like his special suit can compress or stretch the distance between atoms. Therefore, it can go really small by just squeezing the distance between his atoms to small, or get big by kind of ballooning them out. Okay, fine. So just generic sci-fi nonsense, but fine, sure. I'm happy enough for that explanation of how he gets big or small. Now, in the movie, also, there's a bunch of other stuff. When he's small, he can, there's a scene where he's having a fight on like a toy train set because he's small now. I mean, he would still have the same mass, so he would break the toy. But ignoring that, assuming that's also fine.
That's true, isn't it? If he's basically super compressed, he'd be just really, really heavy, wouldn't he?
Yeah, exactly, right? It would just be like a really dense little pellet that's just zipping about. So the scene where he's like running on someone's arm, and that's just the guy whose arm he's running on must be the strongest man in the world, because but yeah, okay, assuming that's also not a problem, the special suit, fine, you get around that, no problem. Okay, the issue is in the movie, now I can't remember if this is in the first or the second movie this happens, but he's told to not go smaller than a certain level, and for whatever reason in the movie this happens. I can't remember whether it's a suit malfunction or for some plot reason he has to. But now here's where it gets silly. He goes subatomic, so he shrinks himself down to at least atomic scale. Now there's a few issues here. So if he's compressing the space between the atoms, how is he getting himself smaller than an atom?
What's he made of now?
What's he made of? Yeah. So just for context, those chemists out there will probably know of Avogadro's constant or Avogadro's number. Now this is, by definition, the number of atoms that there are in 12 grams of carbon-12. Right. So if you have a block of a 12-gram bit of carbon, it will have 10 to the power of 23 carbon atoms in that space.
Okay.
So on average, per gram of material, you have about 10 to the 23 atoms. And what that means is 10 with 23 zeros on the end. That's how many atoms are in, of order, a gram of stuff.
Okay.
So, which means he's got a lot of atoms, right?
That's a lot. Yeah.
That is a lot of atoms. That is somehow compressing smaller than a single atom. So that's a catastrophic fusion event right there. That's not
a
good.
good line. I like it. Yeah.
But yeah, exactly. But also the other thing, which is maybe more subtle, is so when he's at the the atomic scale or the quantum scale or whatever, he can still see stuff, right? At that scale, photons are basically macroscopic, right?
Yeah.
So you'd be hit by a bowling ball and that's your bit of light now. And then you'd have to wait a little bit, and then you get hit by another bowling ball. Oh, that's the second bit of light. You wouldn't be able to see a lot.
No.
But he navigates this quantum realm.
Yeah, and I guess the other problem is you run into a whole bunch of quantum physics problems in relation to, is he now kind of part of the wave function of the universe or something? I don't know.
Yeah,
I suppose we all are really, but
he looks at his hands, but now he's collapsed his wave function. What does that mean for him?
May or may not be there. Yeah, it's kind of a nice imaginative thing, but it's definitely broken down at that point, hasn't it?
A little bit.
Yeah.
And then also there's the for those gravity fans out there, the Schwarzschild radius would certainly be broken. So this is the every mass, every object has what's called a Schwarzschild radius, and basically what this means is it's how small would you have to compress that thing for it to become a black hole itself. So the Earth, I think it's like the size of a peanut or something. So if you compress the Earth down to the size of a peanut, it becomes a black hole. So obviously for a human, it's like a grain of sand or something. But everything with mass has a radius that would mean you're dense enough to become a black hole.
Right.
So this guy, 10 to the 25 atoms in the space of an atom, that's a black hole. There we go.
Well, that's probably why they told him not to do it. In all honesty.
Yeah, maybe, yeah.
That is the reason. But of course, he just disobeyed that and got away with it anyway. Okay, that's just nonsense. But it is a Marvel film. You're talking about a universe where people can fly and, do all sorts of silly things. So, okay. But, I like it. Okay, what else?
So, I don't know if you remember the movie 2012. Now, this came up a lot when I was doing a bit of research for this episode. And I watched it as a kid. And, well, obviously, as a child, I wasn't a scientist. So I didn't really pay much mind to the plot. But reading the plot is so ludicrous, I just had to include it. So this is the setup for why the world is destroying itself. So the sun emits a solar flare from the sun emits a bunch of neutrinos. Now this does actually happen in real life. The sun throws out a bunch of neutrinos, and now apparently the number of neutrinos hitting the Earth per second per square centimetre is about 65 million. So that's a lot of neutrinos hitting the Earth. Now why that doesn't do anything to us is because they're called WIMPs, weakly interacting massive particles. Basically, they're neutral and just their quantum properties are such that they don't really couple to anything. So they kind of just stream through the Earth. Mm-hmm. But the plot in this movie, so the solar flare throws out the neutrinos, but these neutrinos begin to mutate and then somehow start heating the Earth's core as if in the same way a microwave would.
Yeah.
And then the Earth starts to just kind of crack up and do a bunch of crazy nonsense. So you can probably see why that's stupid, because so just remember that number: 65 million per second per square centimeter of the Earth is being bombarded with neutrinos.
Okay.
But just so they've mutated, which now particles can decay and become other things. Even protons, which are quite stable, it decays into like a neutral plus, I think, a positron. So you can conserve charge. So decays do happen, and neutrinos do this thing called neutrino oscillation, where they swap. They can change their color charge, which at some point we can talk about if we do a particle physics episode.
Okay.
But that doesn't mean they now become strongly interacting. But fine. Okay, suppose they do change it to something that is strongly interacting now. And why just that core does it heat? It's streaming through the planet. If it heats the core enough to cause crazy earthquakes and explosions or what have you, it's just going to shred the Earth as it goes by.
Would we not all be sort of irradiated or something before it even gets to the core? If it's going to do that, I suppose. Yeah.
Yeah, it's just... Why bother? Just make something up. Just to call it a cosmic wave. Just make something up. But neutrinos... Yeah,
that's interesting. Yeah. That's kind of... I think this is like the uncanny valley bit of, nonsense. It's like you can accept so much silly science, sort of pseudoscience, and as long as it's kind of works within its own frame of reference, then you can kind of accept it. Yeah. So all this techno babbling in Star Trek and things like that, and you just sort of accept it because it's kind of fairly consistent. I mean, yes, of course, there are things that don't make sense, but it's when it's trying to give you a proper scientific explanation, and they have pretend physicists and scientists there with their white coats, saying the neutrinos have mutated. It's at that point you say, what are you talking about? I mean, 2012 is quite an interesting one anyway, because I suppose you were quite young
I was
running up to 2012.
13, 14 maybe.
Right. So I don't know if you might be aware, but 2012 was supposed to be basically the year when the world got destroyed or reset.
It was the Mayan calendar, wasn't it?
That's it. So it was the end of the Mayan calendar, or at least it was interpreted to be the end of it, and just sort of begins again. So it was supposed to be this thing. And there was lots of people who really believed this. And it was kind of one of the early moments of the bonkers internet that we have now. We had people saying, this is going to happen and that's going to happen. And it was like an end of the world thing. So straight away, that was kind of interesting. And then they made this film. Yeah. And then I've watched it once, I think, and I remember like there was a deep freeze that happened because obviously all the weather got all skewed. But basically, this young family stayed inside with a nice hot fire, and they were okay, And you think, well, it didn't sound that bad, They just had to stay indoors for a bit with their woolly jumpers on, and then they got reunited with their parents later. So, yeah, it is a very bad film.
Yeah.
But also quite funny, I think.
I forgot that was even the plot when I read it. I was like, I can't not say this, but okay, so now this is the last one of the dodgy physics that I'm going to talk about, and it's from the show Three Body Problem, which came out came out maybe this year or last year on Netflix.
On Netflix, it's a book.
I really like it. Yes, I really like it, actually. It's a really good show. I've not read the book yet, but it's on my to read. A lot of the stuff actually in this show is pretty good. So I mean, if you've not seen it, this isn't really spoilers, but early on, they kind of interact with these people who want to solve the three-body problem. So certain people get selected, and they need to solve this three-body problem. And the kind of setup is some hypothetical alien planet has three suns, and it always ends up getting destroyed, basically, because of this three-body problem. And they want to find a solution.
As a physicist, sorry, Thomas, as a physicist, just explain to us very in layman's terms what you mean by the three-body problem. Because I didn't know about it until I saw the show, so I'd never heard of it before. So what is the three-body problem?
So this is a case where you have three gravitationally attracted bodies. So, if you had a three-way system of planets or stars or something kind of orbiting each other. So when you have a binary system, so two things orbiting each other, it's a pretty stable, it can be a stable system. It has a bunch of solutions which allow it, a bunch of orbits that are stable, that they won't kind of fly off and do crazy things. You can kind of define stable orbits.
Yeah.
However, with three bodies, it's now becomes a chaotic system. So what that means is, in the sort of, I guess, the physics definition of the word chaos or chaotic is a system that is very sensitive to the initial conditions. So unless the pieces are put in exactly the same place, the pattern of orbit will be completely different. So it doesn't have an analytic solution. You can't write an equation that solves for a stable orbit. You can numerically do some iterations, but so this is actually, I did a project in my third year for my computing course, or my computing module undergraduate, and it was to code an n-body simulator, basically. So I wrote some code that you could put in an arbitrary number of particles that were gravitationally bound to each other, and then let it run, and then you could see how they would orbit each other in this. So you could choose what masses these bodies have, and you could kind of see how they would kind of fling around each other. And with two bodies that kind of orbit each other, and you can define some stable stuff, but with three bodies, there's a particular problem called the Bourau problem or Bourau's problem, and there's a bunch of papers on it, and it kind of shows these kind of funky orbits that you get. But basically, after a certain number of time steps, these things start to kind of fly off. I should also caveat, it's when the bodies have roughly equivalent masses. Obviously, our solar system is hundreds of body system. So if you ignore the satellites, we have 8 or 9 planets, and then the sun. We're all pretty stably orbiting, but that's because the sun is so much more massive than the rest of the planets. But if you have 3 roughly equal masses, that's when you get this kind of chaotic stuff happening.
I think that's really interesting. That I think a lot of people would be surprised by that, because it doesn't sound like a lot. 3 doesn't sound like a big number. You think, well, surely we have the computing power to calculate that, but it's a lot more difficult than it sounds. Okay, great, thank you for that. So that is the 3-body problem, and in the show there's a sort of scenario that plays out where a planet is in the orbit of these 3 suns, and it just creates chaotic conditions for the people who live there.
So the idea is basically for example, there's one bit where after so many cycles, all the stars kind of line up. So now it kind of superheats the planet, for example. And they're running into these issues because of the chaotic nature of the system. Like I said, you can numerically solve these things. So you could, run a computer and kind of work out after 7 billion periods what's going to happen. But obviously that's computationally expensive. Basically, their issue they were having was, because you can't have a general solution, they couldn't predict what was going to happen after so many cycles, after so many self orbits. So that was the problem. It wasn't that they couldn't figure out what's about to happen. It was they didn't have a solution that would tell them what was going to happen forever. That's the problem. So they explain that pretty well, and that they show some people's methods to try and solve this problem, and I like it. So it's a pretty good show. And there's a bunch of other stuff as well in the show that I actually quite like from a sci-fi point of view. I can kind of suspension of disbelief. I can be like, I could believe that could be a thing. So the issue I have is, and now this is a bit of a spoiler for the show if you've not seen it, but at the end of the show, or near the end of the show, the baddies kind of reveal that they've been using these, I can't remember what they call them, but these super particles to kind of mess with things on Earth. So they were kind of messing with all the scientific experiments to make the results kind of nonsense, and they were making people see things that weren't actually there. And it was kind of a threat. It was like, we have all the power to do whatever we want, to kind of just do what we say, basically. And the way they kind of explained how this thing worked was they had these 2 particles that they entangled and then sent one to Earth and kept one on their planet or their spaceship or whatever. And because they're entangled, what you do to one, the other one also does. Now, this is a thing that is in quantum mechanics. You can entangle quantum states. Theoretically, at least, you can have them infinitely far apart, and they're coupled in such a way that if I flip one, the other one also flips simultaneously. Right? Cool. That's a pretty neat little system, and it's a good little MacGuffin to have in a sci-fi story.
Yeah.
The caveat to that is, like all things quantum, once you interact with the thing, you've now broken the quantumness of it. So if you have two entangled states and you alter one of the states, the other one will do the same thing, but to know it's done the same thing, you have to measure it. Therefore, you collapse the wave function and break the quantumness. So you've disentangled these particles by doing that now. So you've done a cool thing, but imagine that you can do it once. You can do one action per entangled state before the entanglement's broken.
Okay.
Well, if you want to look at it, that is. Okay.
Yeah.
But let's suppose they've got around that. They have super quantum knowledge, and they actually know how to not disentangle when they do that. Fine, okay. So they have a method of basically moving this particle around, basically at light speed on a different planet when they're ages away. Fine. But one of the things in the show is one of the types of experiment they're messing with are particle physics experiments. They're kind of sending this super entangled particle into the colliders and knocking all the particles around, so the data is just unusable. So basically they're halting the progress of science on Earth. So here's where I kind of draw issue with. So again, suppose they can have two entangled particles and they don't break the entanglement, and fine. You're sending something particle size, of order proton scale, into a particle accelerator and knocking things around. Now, particle accelerators are extremely energetic places. I mean, these things, they like crack protons apart and they spontaneously generate particles from just the energy in the vacuum. The crazy energies. And you're sending in your delicate little entangled particle into these, It would be like, imagine throwing a paper aeroplane at a train to try and knock it off course. That's where I have issue. They, showing people images in their brain or whatever, okay, whatever. But you're going into, these super relativistic particle states. Crazy stuff happens in these accelerators, and you're just, knocking things around and not damaging your really delicate system. A little bit
interesting. That's very good. I would never have thought of that. That's very good. Okay, that's got me thinking about another episode, because there's a really interesting sort of psychological question about the psychology of aliens. So if we did meet aliens, how could we relate to them, and how could they relate to us? There is a sort of storyline in the show that is a kind of fascinating idea. I won't mention it. It's kind of, I think, an important spoiler. We'll do a spoiler-filled episode at some point, I suppose. But there's a psychological element to us as human beings that they don't have. That creates a sort of massive problem. And I think that'd be quite an interesting one. There are a few psychologists who are thinking about what would happen if we met aliens. How would we interact with them? What sort of protocols? I don't think there's enough of that happening. I mean, the likelihood of us meeting, I suppose, is very, very, very unlikely. But still, it feels to me like an interesting and important question. But that's for another show. Okay, good. Let's move on then because of time. So
yes.
Another one that you like. Tell us another one that you like.
Yes. So these are onto the good science now. So I can't do a movie physics without talking about Interstellar. I love this movie. It's probably one of my favorite movies. And what I didn't realize actually until again researching for this episode, a lot of keyboard scientists, shall we call them, are really mad about the movie. They really talk smack about the movie. Specifically the ending, which is the most pseudoscience-y bit of it. But I thought everyone liked it. I really like it.
Kip
so
Thorne was involved, wasn't he? Kip Thorne was involved in the making of it, I believe.
Yeah. There's also a book actually, a book which is, I think it's called like The Physics of Interstellar, and yeah, basically it's a bunch of physicists kind of talking about the stuff the research that went into it, basically. I mean, even to the simulation of the black hole, like that's just very cool.
Yeah.
But yeah, so Interstellar does some really good stuff. I think it does a nice job at introducing relativity for kind of a layperson audience, even if they do have the corny fold the paper and put the pencil through it.
Can you believe it? How many sci-fi movies do that? Oh my god! And it's always like one scientist explaining to another scientist how that works. No, they wouldn't have to do that. Anyway, carry on. Yeah.
Anyway,
sorry. The bit that I love in that film is that they've got a whiteboard. I'm a trainer, so I love whiteboards. They've got a whiteboard on the spaceship. So he flips over a monitor, and on the back of the monitor is a proper whiteboard, and he's got a pen and everything. I just think that's brilliant. That is my sort of spaceship. Carry on.
Yeah, I like it. But yeah, so one of the neat little things that I liked in it is the fact that the wormhole that they go through is a sphere. I really liked that because so obviously normally when you see it, it's either the little analogy of the paper through the pencil, or you see a drawing of it. Obviously, most of the time when you see sort of, I guess, gravity demonstrations, a common one is the torch sheet with a bowling ball in the middle.
Yeah.
Obviously, that's a 2D representation of a 3+1 dimensional thing. You can't really, I guess, what it might closely look like is a mesh with kind of a 3D mesh with sort of contracting or expanding grid points, but it's kind of hard to visualize that. But so obviously, on a 2D piece of paper, a wormhole is just a hole through it, right? Yeah, a hole through the flat surface. But a hole is a circle in 2D, but in our world, in the three-dimensional world, a circle is a sphere. So the fact that the wormhole is actually a sphere that they kind of orbit around and kind of fall into, I really like that. Whether that's what they would actually look like, I have no idea. But I thought it was cool because obviously it wouldn't just be a hole on a flat surface because space isn't flat. It's a three-dimensional thing.
Yeah.
So I really liked that. That was really cool. Obviously one of the things, kind of the sort of climax of the movie, he kind of falls into the black hole, kind of drives into the black hole, and then there's some time travel stuff going on. Obviously that's the most ludicrous part, but I'm going to ignore that because it's obvious that's just kind of make believe.
This is the Tesseract, isn't it, that he ends up in?
Which it's a cool visual. Obviously I say it's inaccurate. We have no idea what's inside a black hole, so maybe it's exactly like that. But I'm not going to talk about that because that's obvious. The thing that I think is one of the most unrealistic things is how quickly they go from a fundamental theoretical discovery to practical application. So when Matthew McConaughey's in the Tesseract, he kind of does some Morse code with the books on the bookshelf, and then Murph, his daughter, figures out the code, cracks the gravity problem. I can't even remember what problem they're trying to solve, but whatever the gravity problem is, they solve it. They solve the equation. We've cracked it. We now have a theory of gravity that's all encompassing. Cool. And then in the span of 20 years in the movie, they've built this space station, the Ark basically, and they're now traveling through space with artificial gravity and all this stuff, which is cool. But going from pen and paper theory, it might be an amazing discovery, to then building artificial gravity spaceship. I feel like there's a lot that has to happen in between then.
Okay, so this is in between Murph growing up. They've created all this technology and engineered it, and they're now in space on this sort of arc, as you say. Yeah, that's a good point. I never thought about that. Yeah,
because at the end of the movie, she's quite an old lady, so she's aged. Let's be generous. Say 60 years. She's aged.
Yeah,
60 years to go from complete super theory quantum gravity to working spaceships with artificial gravity and clean internal atmospheres. I just think that's
a
little bit
I suppose
unrealistic.
they're desperate. They need to get off the Earth because it's dying. So maybe that's the rocket up the backside that they needed.
Maybe. Maybe. Let's say it's that.
Yeah. Okay.
Okay.
But I love the film too. I think it's it's got a great mixture of filmmaking and there's just some scenes in it that that affects me personally in a way that most films don't. So there's a beautiful scene where it's sort of almost silent. There's a piano, I think, playing, and they're just going past Saturn. You see the rings, and it just makes you feel cold. It just has that, because you sort of feel the coldness and emptiness of space at that moment, and that is just beautiful filmmaking, I think.
Yeah, I think it's a great movie. And if you've not seen it, I don't know what you're doing. You should watch it. It's great. Okay, so the final one now. And this is a fairly recent movie, The Invisible Man, the one that came out a few years ago. So I think it's 2020, I think it came out. And it's got the lady from Handmaid's Tale in it, I think.
It has Elizabeth Moss.
Yes. So I quite like this movie. But the coolest part is obviously the Invisible Man. So in this movie, I don't know how it is in the original story, but in this particular movie, he's like a tech guru or some kind of tech whiz. And he makes his suit basically out of lenses and cameras. So the suit projects what the cameras behind him are seeing and so on. So it kind of gives the illusion that he's invisible, but he's just kind of showing you what's behind him. So that's pretty cool, and that makes a lot of sense. I mean, you could kind of argue, okay, the suit will be really delicate, and I mean, there is a point in the movie where he kind of like dinks himself on something, and suddenly now
it's damaged.
It gets damaged. So they kind of talk about that. There are some issues with having such a technically advanced thing, but overall, I thought it was a really cool way around making somebody invisible, and it makes sense, and it's within. I can imagine something like that happening in the next 10 years.
Well, they have created some effects like that. I've seen some images of like tanks that have cameras that, as you say, just basically create. I mean, they're not completely invisible. You can see that there is a screen on the front of the tank or at the side of the tank, but from a distance, you're not going to see it very well. So it's actually quite a good way of doing it. So it's not bending light or anything like that. It's just literally projecting what you would expect to see behind it on the front of it. So yeah, clever.
Yeah. So yeah, that's cool, and yeah, but it's a nice segue into what I actually want to talk about. Whenever I think about this movie, I think about this paper that I read. It's from about 10 years ago, and it's published in Nature Communications. So Nature is one of the highest impact journal. So it's a very reputable research journal. And the title of the paper is Image Transmission Through an Opaque Material. So this is very cool. Basically what these researchers from the University of Paris.
So I've got a fly attacking me here. Being attacked by a fly. Carry on.
Yeah, they managed to shine an image, or I guess project an image onto an opaque material and reconstruct it on the other side. So basically projected an image through an opaque object they managed to do, which sounds like sci-fi. And when I first read it, I was like, this is crazy. It's not a particularly complicated image, but they project an image onto some kind of zinc crystal powder. So it's opaque material, I suppose I should say. Now, obviously, in everyday language, opaque means not transparent. So the opposite of transparent, right? Now, opacity, specifically in this kind of field, or I guess even in what I'm doing, has some very specific definitions. But basically, you wouldn't be able to see through it with the naked eye. Imagine if you had like a jar of sand, you can't see through the other side. Yep. So it's a opaque material. It's called a it comes on a granular media, so like it's a powder. And basically, what the kind of idea behind this is that so they project an image through it, and they use the principle that all the light is scattered, not absorbed. And the image you see on the through the back of the material, it's just like a pixelated, noisy image. But they basically say, imagine it like a billiard ball model. Imagine you've got, you've got a snooker table, and you've got a bunch of posts, and you knock all the balls. They're going to bounce off the posts. They're going to bounce off each other. Well, I mean, light doesn't self-interact, but for argument's sake, it kind of bounce off all the stuff in the way, and then when they get to the other side of the table, they're going to kind of be in a scattered jumble mess. So, because nothing is lost there, it's just been reoriented.
Yep.
The idea is there must be a transformation has occurred. So I've got my input, there must be my black box that then turns it into the output. If we can work out what is inside the black box, what that transformation is, then we can reconstruct the image. And that's what they do. So I've mentioned before on a previous episode something called singular value decomposition or single value decomposition. And this is basically if you have, normally it's used in image processing or signal processing. So if you want to compress an image, for example, you can perform SVD on it. And basically what you can do is you can break an image of something up into its constituent parts, whatever that may mean. And then you'll find out that, for example, most of the image will be built up by this part of the signal, and then the next biggest chunk will be this signal, and the next biggest chunk this signal, and it'll kind of drop off. And then you could, in principle, cut off the bottom 20% of the constituent signals, reconstruct the image, and now it's considerably less data heavy.
It's compressed, yeah.
It's compressed, but it still retains, similarity. It's the same. And you can do that with noise removal, for example. Like some noise removal softwares, you can kind of do this. You can break up the sound wave into the constituent pieces, be like, okay, this stuff, I don't want to keep those frequencies.
That's how MP3s work, isn't it?
Yeah. So, so it's an interesting principle. But yeah, the thing there that you want is you need the transformation matrix. You need the thing that transforms the input into the output. It's called an inverse problem. And there's many examples of inverse problems. But this is kind of what they do. They specifically how they work it out, I'm not entirely sure. I've read the paper a couple of times, but this isn't the kind of physics I do, so sure. A lot of the stuff is kind of a mystery. But yeah, they project an image through this powder, and then on the other side get basically a pixelated mess, and then they work out what the transformation matrix is, and then they reconstruct the image from the pixels. So what I like to think of is, you could make an invisible man using this technique. Like I say, it's a bit more sci-fi than what they actually do in the movie. Yeah, but I just thought it was really cool that that a team actually physically did this, and there's pictures on the paper of it's like a little flower thing. But yeah, shining.
I'll see if I can get some images. Maybe if you've got some, send me. If you know where the articles are and everything, and send me the link to the paper. Yeah. I'm not sure whether everybody will be able to access it. Some of these things are behind paywalls, as we've said before, but send me the paper and or the link to it, and or at least the reference, and I'll put it on the Facebook page. Don't forget to join the Facebook page, folks. Okay, very good. Yeah, that would work. The Invisible Man is an interesting film. I've actually done I every now and again I do my own little podcast called Cults on Film. So I'm interested in how cultic relationships and groups work, and actually that film is it's a kind of allegory for a coercive relationship. So put aside the fact that it is sci-fi, and The Invisible Man is an old story. It's actually the idea of invisible people has been around a very, very long time. But the way that particular film is written, it's actually a story about coercive control, and it's got all the elements in it. So it's a very interesting one. So maybe check that out if you want to. Okay, great. Well, we've gone for an hour and 20 minutes.
Yeah. So
we're probably there. Is there anything else you wanted to say before we go?
No, those were sort of the main ones. Like I said, I got the goofy ones out of the way at the first, and then some of my favourites. But yeah, so hopefully that was enjoyable.
I guess I don't know if there's a way to summarise it all, but we love science in movies. And there's obviously lots of physics in movies. There's, if you think about something like Jurassic Park, there's biology, and there's all sort, and there's loads of psychology. We looked at that last time. And I guess I think it's okay to play a bit fast and loose with these things, as long as you respect it in some way, So you're kind of showing some understanding that it's based upon something at least. And then, of course, you've got the fantasy stuff, which you don't have to worry about science at all. If you want to believe in dragons and elves and nymphs, then that's absolutely cool. That can be part of your storyline. But if you're going to call it science fiction, then it has to have a bit of a root in science, I think.
Yeah, I definitely agree with that. Yeah.
Okay, very good. Well, thank you very much, Thomas. Thanks for listening, everyone. Don't forget to like, subscribe, and write a review. Why don't you? And we'll see you again for the next one. And by the way, it's every fortnight we're doing this this podcast now. We struggle to do it every week. We're just busy, and every fortnight means we can keep it going for longer. The seasons can keep going a bit longer. So, see you in a fortnight's time. Bye for now.
Goodbye.